When we finished doing the Newton's law stuff and we were introducing energy and momentum, we talked about the things that were in common when two things interact. And so they exert the same magnitude of force on each other, and they exert that force, that force on each other for the same amount of time. So let's actually work through that. So I'm going to have two objects interact. So the force on A from B, so this is on A from B, is equal to the negative force on B from A. This is Newton's third law in shorthand form. They do this over the same amount of time, so we'll just multiply that. So the force on A from B times the amount of time that they interact should be equal to the negative force on B from A times the amount of time. And this is the total force that A exerts on B. Let's just close this up and so that there's only A and B in this universe. What does F equal?
Force.
That's what it represents. I was thinking of the second law.
Is it 1? Is it 1? Because it just stays the same.
No, not looking for anything that specific. Newton's second law. F equals.
MA.
So this would be the mass of A times the acceleration of A times time is equal to the negative mass of B times the acceleration of B times time. Well, what is acceleration times time?
Is it acceleration times time?
Yeah.
That's
It's velocity?
Very close.
Change in velocity.
Yes. If you recall, acceleration is the change in velocity. Change in velocity over the change in time. So if I do acceleration times time, I get change in velocity. So this is mass of A times the change in velocity of A is equal to the negative mass of B times the change in velocity of B. I'm going to now write it out. I'm going to put a bunch of subscripts in here. Try not to choke on the cough drop I have in my mouth. So I have mass of A times final velocity of A minus the initial, I prefer that, but probably flip back and forth. Final velocity of A minus the initial velocity of A. These are still vectors. Is negative mass of B times the final velocity, VB final, minus VB initial. I'm not going to distribute because I know where I'm heading on this. So I have mass of A, V, A final, minus MA, V, A initial is equal to negative MB, VB final, plus MB, VB initial. So incredibly obvious, I'm surprised that this is not kindergarten stuff. We're gonna make one other change. Or I'm going to get all the I's on one side and all the F's on the other side. So bring this over to here and bring this over to here. And at that point, everything will become clear. Or not. So I've got, actually I'm going to do that and then I'm just going to flip sides. I'm going to do two steps in one. So I get MB plus MAVAI equals MBF MB VBF plus MA VAF. There we go. Give you a moment to catch up and just marvel in the beauty of that. All right, so here's the question. What's so marvelous about this? Why should this be marveled?
We indeed derived it.
Yes, we did. That's why it should be marveled. There's another reason. Perhaps it answers the question of why we derived it.
So we can use it with
All right.
more stuff.
Yes, that is true as well. We can use it with more stuff. All right, let's think about the impact here. I got the two objects A and B. I got a universe with just A and B in it. I now have this quantity here, this mass times velocity, that if I take the total initial value, it's equal to the total final value. It doesn't matter what happens while they're interacting. All that matters is what's happening before. I know that total is going to be what I have afterwards. In physics, it's called a conservation law. Also, writing MV down 4 times is kind of a nuisance, so we're going to change that. I'm going to use a letter we haven't used yet, I don't think. I'm going to use P, of course, to represent MV. So this just becomes P, the initial, plus P, A initial, is equal to P, A final, plus P, B final. And still, potentially, this is just too much to write, so instead of just having all these little p's here, I'm just going to use a big P to represent the total there. So big P initial equals big P final. Now, it's very difficult how I write my p's, tell the difference between uppercase and lowercase, other than relative size next to something else. However, generally, when you, the notation is the big letter represents the sum of all the little letters. This P, of course, has a name that I have read once about why they actually use the letter P. I forget what it is, but this is momentum. If you want to be very pedantic, linear momentum. This is the shorthand notation for expressing conservation of momentum. Total momentum before equals the total momentum afterwards. It's similar in respects to dealing with conservation of energy laws. The disadvantage of momentum is you're dealing with vectors. The advantage of dealing with momentum is that you're dealing with vectors. The math is more difficult because you're dealing with vectors. However, you don't lose that information. With the energy, you lose the information about direction. So there are pluses and minuses to both. All right, so let's just do a simple example here. Got a 2 kilogram mass going at 4 meters per second. And I have a 3 kilogram mass going at 5 meters per second towards it. They're going to crash head on. What is the momentum of the 2 kilogram mass? Wait, say 8 meters per second times kilograms? Oh, yeah. Otherwise, that is 8 kilogram meters per second. So, and I'll do a subscript related to somehow differentiate them. So P2, particular mass, is 2 kilograms times 4 meters per second, and 8 kilogram meters per second. Are you happy with that, Ali?
Yeah, wait, no,
You're not happy with it?
wait. I think it's kilogram times meters.
Yeah, I mean, I think you said meters per second times kilograms. It's the same thing. Not too far. Anyone want to debate this? All right. What is the initial, this is the initial, the P3 initial. What is the initial momentum of the 3 kilogram mass?
15 meters per second. That's a 5 and a 3, 15 meters per second.
Somebody want to correct that?
15 meters.
Negative 15
All right, that's one correction.
meters
Negative,
per second.
negative 15 kilogram meters per second.
Okay, I didn't hear either of you say kilograms. So, yeah, negative 15 kilogram meters per second. So when I asked Ali if he was satisfied with it, what he was doing was establishing the positive direction. He could have just as easily said that that was negative 8, making this positive 15. But they are opposite signs because they're going in opposite directions. So Ali, when he said 8 here, he established to the right is positive. And when the rest of, and when no one objected, the rest of you were in on the conspiracy. All right, so what is the total initial momentum?
And like the whole thing, like both blocks.
Yeah, the total.
7, negative 7 kilogram meters per second squared. Meters per second, sorry. Kilogram meters per second.
What's a kilogram meter per second squared?
Something.
Yes, it is. What's a kilogram meter per second squared? Yes. What's a kilogram meter squared per second squared? I think so. What? That's kilogram meter per second. I'm talking an extra meter and an extra second. Kilogram meter meter squared per second squared.
Is it joules?
Say it with G?
Is it joules?
Yes, it is. It's joule. Kilogram meter per second, though, they haven't bothered coming up with a shorthand for that. There's no one-word unit for it, which is a cursing and a blessing. The curse is that you might just be writing kilogram meters per second every time you have to put down units for it, which might be a little bit too much writing. There's one shorthand that you can take. Notice that we started here, and we didn't change signs, so at this point, it's the same thing. This right here is just the final momentum minus the initial momentum. So this force times time is just the change in the momentum of A. So the units of momentum have to be the same units as this. So a Newton second also works. However, a Newton second might, some days might feel like too much to write. So you are allowed to make up your own unit. But there are rules. 1, don't use a unit that is already being used. If your name is Nick and you want to honor yourself with a capital N, don't. It's already being taken by Newton. It doesn't even have to be an actual letter. I've had some students create their own squiggle. What I will often do is I will use D, and I will define it, that's the 3 lines there, is a kilogram meter per second. And once I've written that up, I can now write this as negative 7D. If I erase that, before I erase this suddenly becomes wrong. Because since this is a unit I have made up, it is a unit that is only valid as long as it's defined. And I picked D for Descartes. Descartes did while Newton was pursuing the idea of forces, Descartes was looking at momentum, what we now call momentum. I think he's the one who used the letter P to start us off from that. Descartes D, I think, therefore I am guy. All right. Questions here before we extend this problem? Another vocab word. This force times time, or the change of momentum, has its own name. And possibly my most obscure clue of all. When someone suddenly buys you flowers, that is called if you ever get flowers from Ali, you now know what that means.
Gift.
It's as if none of you were watching television commercials in the 70s. It was a perfume ad for Impulse.
Gosh darn it. I ain't use line anymore.
The key there was the sudden aspect. So, I made the claim that momentum is conserved, but over there we've got this word for the change in momentum. How can there be a change in momentum if momentum is conserved? Well, we do need to categorize one more thing. Momentum is conserved. This is true in a closed system. There are no external forces acting on the system. And system is whatever you're looking at. So if I'm over here looking at this, if I look at just the 2 kilogram mass, it is a closed system until this hits it. As soon as the 3 kilogram mass hits it, it is no longer a closed system because we now have this outside influence. If I define my system as both of these things, it stays a closed system because there's no other object. This universe consists of just these 2 things. So assuming that these are the only 2 objects in this universe, closed system, they're going to collide, they're going to change their velocities. What's the final momentum?
Same thing.
I have asked that on the test. I had these 2 things going like that. First question, what's the momentum of this? What's the momentum of that? It's total momentum. And the next question was, what's the final momentum? Shocking number of people missed it, even though they had just done the math. Now, how it's split up, we don't know. I have to give you some more information. So what I'm going to do is give you more information here. They are going to stick to each other. Now, that's too many words, of course. This is referred to as a perfectly inelastic collision. So on the next test, there will be a question where there is a perfectly inelastic collision, and you need to know that means they're going to stick together.
You said stick together was too much words.
We have one fewer word, more letters, but one fewer
Oh,
word.
I see what you're saying.
So when they collide, it's now a 5 kilogram mass going at some velocity. Well, I know what the total is. It's -7. So I have 5 kilograms times final velocity is equal to -7 Descartes. What is my final velocity? through a lot of extra letters in there, let me rewrite it in the math, as math would write it. 5x equals -7, that's the math problem.
27.
Whoa.
That seems out of the blue.
7 over 5.
It's almost like a math Tourette's.
Negative 1.4.
Yes. I'm not addicted to a calculator, it's not anything. Units,
Meters per second?
now, as they interact, the force that they're applying to each other is not going to change, because they start out not touching each other, so the normal force they exert on each other, of any appreciable size, the normal force they exert on each other is 0. They're gonna hit, that normal force is going to increase up to a certain amount, and then it's gonna, well, and then they'll eventually go to the same velocity if you consider it one object. So the force being applied is not constant, and therefore using Newton's second law becomes a lot trickier because the force is not a constant. But it doesn't matter when we're dealing with conservation of momentum here. Let's take it another step. What is the impulse on A? Or on, sorry, not A, 2. On the 2 kilogram mass, what is the impulse?
Is it the 3 kilograms? That like push up for like when it connects to each other?
We're missing a.
No, looking for a number here. Ultimately, it's change in momentum. So if I ask you what's the impulse of the 2 kilogram mass, I'm asking what is the change in momentum of the 2 kilogram mass? In other words, P final minus the initial. Well, the initial we know, that was 8.
Yes.
And I still have Descartes to find, yeah. What is the final momentum of the 2 kilogram